recording. Okay, so we have this notion of, we've looked at Python and uncertainty. There's some problems on some programs on Piazza that you can get to play with this side, and we'll come back to those every now and then. And then the idea of a probability experiment, its outcomes, and the idea of events, which are sets of outcomes, and the sample space, which is a set of all possible outcomes, and the events, which are subsets of sample space. And the next topic we want to deal with is probability models, where we begin to give a model of, we know that when we toss a coin or roll a dice or other events, that there are certain patterns that occur. You have a sense that somehow neither heads nor tails is more likely to appear. And so if you looked at a long chain, then they would appear about one half the time. But so the goal of the probability models is to predict patterns. And let's look maybe at some of these so here's one of the first programs, coins1. And all this Python program does is to import the random function, random int, so we can model a coin. And this is going to model a coin flip. Now we can flip the coin many times. So it's going to have a loop here for experiment in range 0 through flips. It's going to toss the coin, and it's then going to build up a pattern of heads and tails. So you can see, so let's see if we run this, how many coin flips. Let's say 10. Let's see. Well, here's the pattern here. We just get, you can see here, heads, tails, 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 heads, heads. Let me see if you can maybe put this up a little bit. Okay. So now, one of the interesting things about, if you tried to write down a sequence of heads or tails that was random, actually that's very hard to do for a person, because what you would want to do is, you sort of think that randomness means that you need to mix up the heads and tails. And you can see here that what one feature of a sequence of outcomes for a probability experiment is, you also randomly have sequences of the same type of any length. So if I come up here and run this again, and I put, say, 100 flips in, then you can begin to see not only that it flips back and forth with heads and tails, but you also have these really long runs of heads and tails. And that's typical of that. Not only is it random between heads and tails, but you also have randomly equally likely, you have sort of randomly likely different runs of heads or tails. And you could maybe do this again and look at 1,000, and you can then get lots of outcomes. And you can sort of see that there's in here, you're beginning to pick up, like here's one here of a long run of heads all the way through. So it's not that unlikely to have long runs of heads or tails. Okay, that's this first experiment. And then I have in this packet, there's like 2 coins ones, 2 dice ones, and a puzzle we'll get to at the end of the chapter 8 here, which is the Monty Hall puzzle. So let's look at the second one, because this, I want to open that. Okay. So now we have the second experiment. And what this does is, this, instead of displaying the result, it's going to just tabulate, say 1,000. And here you had, after 1,000 coin, it's counting up. Well, this is just one. The actual distribution here of heads and tails is actually interesting. You can see I made this comment about having lots of tails and heads, but so this idea that there's half of them are heads and half of them are tails is a little bit misleading as to this actual distribution of heads or tails. So this is the kind of pattern that is interesting in probability, as well as the fact that you have you begin to have sort of 50%. You can see that in the experiment, you can see that somehow it's equally likely that you're going to get a heads or tails because this is beginning to be very close to 100. Now, if we did then 10,000, then like this is only 6 away from 500, and this is 6 more. Now this one is 40. Half of 10,000 is 5,000. This is further away in magnitude from the halfway point of 5,000, and this is a little bit closer. You know, that's got 40. It's like 45. Well, it's a 45. You've got 45 extra ones here, 45 less heads here. So in magnitude, it's less than it's greater deviation than over here, but percentage wise, like if I take 506, if I take say 494 to make it real division, or it'll be real division anyway, over 500, well, that means that it's well, what I want is not over 500 but over 1,000. Then it's like close to 1/2 or 0.5. But if I do 4,956 over 10,000, I'm getting it's like it's the same. The interesting thing is to look at the percentages, because I'm getting this percentage is this is almost equal to 1/2. So if you stop looking, even though this is further away, it's equally, it's like percentage wise, it's very close to 1/2. And that's what happens with a lot of these probability experiments. Let's look at then the next one, which is the dice one. Okay. Oh, forgot to open it. Let's get that open. Okay. So now we have a dice one, and this sort of does the same thing with dice that we have. Let's say we have 100 rolls of the dice. Now, the probability experiment here wasn't, let me make this larger. The probability experiment was not just what's the probability of 1 through 6. What's actually is here's the, let me go back here and show you what the probability experiment is for this. Let's say that we roll, our probability experiment is to roll 2 dice. Okay, if you roll 2 dice, then what we're interested in is, what we're looking at then is the events of the sum being 2, the event of the sum being 3, up to the sum being 12. Because if I have 2 dice, the smallest sum I could get would be 1 plus 1 is 2. And then I'm going to get everywhere up to 6 plus 6 is 12. So if I'm thinking of the probability experiment of looking at rolling 2 dice and then looking at the sums as my outcomes, well, these sums, even though each roll of the dice, you may think, well, it's equally likely to be a 6, the sums are not equally likely. And that's what this probability experiment does. It's got it in this array here, this list. It's recording how many, in 100 rolls of the dice, how many outcomes do you have for the sum being 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Well, I think it's like 2. I'm not sure why we must have miscount. Anyway, the sum is probably the sum is 2 through 12. I miscounted, obviously. That you've got, see this, so that don't worry about the probability. This is just the frequency of how many of them occurred at different numbers. So for example, you can see here that the sum is 7 is like the highest one. So that if in some sense the pattern is that the 7 is if you roll 2 dice, the most likely outcome for the sum of the 2 faces is 7. And that might not be obvious. And I think, let's see if I do let's look at the next one. And this one is trying, let's see if this works. How many rolls? Let's do 100. Okay, what this one does is it makes a nice graph. So you can actually visually see for 100 rolls, how many, this is like how many, these numbers here show you how many were in each sum. And then let's try doing it with more rolls. Let's just run it again this way. Okay. How many rolls? Let's do 1,000. Okay. Well, here you can begin to see that we're getting this pattern here where the 2 and the 12 are less likely and the 7 is the most likely. So it's beginning to fill out a pattern. And one of our goals would be for this experiment to understand why this occurs. Why is it that the 7 is the one that's most likely to occur? And what do we mean by these probabilities? Okay. Well, so run these experiments and play with them to see, with some big numbers and try to see what's going on with them. For that last one, you may need to do that in Vera Virtual, even if you have Thonny running natively, because there's some other libraries it uses that you might have to install to get Thonny working. Okay, to get the graphical stuff working. Okay, so now we have that experiment, and we want to go on and talk about probability models.